So the next topic we're going to talk about is the networking layer. So last time we spoke about layer 2. The networking layer is layer 3. And like we said at the beginning of the last lesson, again, the key points, the protocol data unit is the packet. Okay, so anything we refer to as the network layer is the packet header, the packet addresses, the what's in the packet, etc. And also the addressing information we use at the network layer is IP address. Okay, so this is where we get into the interesting part, and this is where we'll probably spend a little bit more time on this layer than others, because you'll realize that in the next couple of weeks, let me just find in the next couple of weeks, we're going to look at network layers today. Then we're going to look at address resolution, which is to do with, again, TCP/IP. With the IP addresses, IP address resolution, that is. And then after that, then it's the basic router configuration to do with configuring the router to route IP addresses. And then we're going to look at IP addressing, subnetting, and then IPv6 a little bit, ICMP, which is again using ping protocol to sort of ping IP addresses. So you can see it's quite a few topics, all to do with layer 3. Because that's the main thing we're going to concentrate on in this subject. Layer 2 we've looked at, fairly straightforward, connects things together, uses MAC addresses, okay? Our switches. But the main thing is the layer 3. That's where we'll be configuring the routers to route between different networks, and also using that routing information as well as seeing it work in real practice. So let's get into it. The networking layer, we're going to look at the characteristics, the IPv4 packets, IPv6, but really with the IP6 we're going to really be very quick with it. It's the IPv4 we're concentrating on, and we're going to look at how host routes and the routing table itself. Remember that question before in the first lesson? Where is the IP addressing information kept on a layer 3 intermediary device, the router? It's in the routing table. Okay, that's where we have a list of all the networks we know about and how to get there, how to forward it on. So let's look at the characteristics. So the networking layer provides services to allow end devices to exchange data. IPv4, so that's version 4, IPv6, version 6, are the principal protocols of this layer. There used to be other types, but these days it's streamlined down to just IPv4 and IPv6. There used to be like AppleTalk, IPX, SPX, and all this other types of protocols, but don't worry about them too much. It's just IPv4 and 6. The network layer performs 4 basic operations. It addresses end devices. Was that someone's hand up or something? No? It addresses end devices. It does encapsulation. It does routing, and it does decapsulation. So we already spoke about the term encapsulation. Encapsulation is basically you get your letter, you put it inside an envelope. It encapsulates the letter in the envelope. If we put the envelope in another type of envelope, in a parcel, then we're encapsulating that again. And you can see that if you remember, we have our data at the application layer where the users use. We generate the data, we send it, goes down the OSI layer into the segments, which is the layer 4, into packets, into frames, and then into binary at the physical layer. So each one of those layers, the segment is encapsulated in the packet is encapsulated into the frame. So it's a bit like the parser where you've got extra layers of wrapping each layer. And decapsulating is basically opening up the letter, opening up the parcel and unwrapping that layer and seeing what's in the previous. So IP encapsulation. IP encapsulates transport layer segment. So no no prizes for guessing what's the protocol data unit it's called at the layer 4. What do you think it is called? Segment, exactly. What do you think in layer 4? What do you think we use as addressing? Okay, we sort of alluded to it a couple of times already today, and as well as previous lessons. What do you think we use it? So layer 2 we use MAC addresses, layer 3 we use IP addresses. What's layer 3? Layer 4? Protocols. Yeah, you're on the right track. Those protocols like HTTP, HTTPS has what? Remember the numbers I showed you? Port numbers, right? So ports. Okay, so layer 2 uses MAC addresses, and it's called a frame. Layer 3 uses IP addresses, and it's called a packet. Layer 4, we use port numbers, and it's called a segment. Okay, remember those same things, same sort of important things? We need to know all of that. Just don't, I should be able to go up to you on Sunday night after you've been partying and ask you what's a layer 4 protocol data unit. You should be able to tell me it's a segment. Okay, that's a level I need you to know it at. All right, so let's not skip ahead. Let's stick with layer 3. So we use the IP address and we call it a packet. The IP can use either IPv4 or IPv6. They're just different versions. And I think we've shown you that IPv4 is the dotted decimal notation. So which means it's a number, dot number, dot number. There's 4 numbers, right? 4 octets. And it's called octet because each one of those segment areas is made up of 8 bits. Okay. IPv6 is not the dotted decimal notation. It's actually a hexadecimal. So let me just quickly show you an IPv6 IP address. So ipconfig. Let's go right up to this. So we know that this is our IPv4 IP address. You can also see there's an IPv6 IP address. What do you think that is? Yeah, it's not binary. It's not decimal. What is it? Hexadecimal. Yeah, because we can see that it's got the letters and numbers. So that's hexadecimal. And obviously this is the decimal dotted notation. So obviously there's a number, dot number, dot number, dot number, 4 octets, 32 bits for the whole IPv4 address. And with the IP address, there's also always comes with a subnet mask as well. And even if you don't have a gateway, even if you don't have anything else, you have an IP address and a subnet mask. And we'll look at how that works in a second. Okay. So the IP packet will be examined by all layer 3 devices as it traverses the network. So layer 3 devices are the routers. Okay. So if I think we've talked about this, how if my computer wants to talk to a computer like Google, it will have to go through our local gateway. And obviously it's not directly connected to the TFSA network. You'll probably have to go to various locations around the place. And let's try path ping. So not. Yeah, path ping will do it, but the tracer will do it as well. Google.com. And let's talk about this. So basically, this is my computer. This is my local gateway. But beyond that, each one of this is a different layer 3 device or router. Eventually, getting me to this device, which is probably the Google server, www.google.com. So if you look at this, there's all of these routers in between. So it's just like if you think about, I'm going to drive to Melbourne. Which roads do I need to go? So I need to turn right onto the Glen Osmond Road. Then I need to go down the Princess Highway. Is it freeway or highway, whatever, the freeway. And then I have to turn at Taylor Bend, and I then go on this road and that road. I don't even know the road, so but there's always multiple ways to get there as well. You know that if the main road down at Taylor Bend is got roadworks, you can circumvent it by going another road. So that's the whole point of these routers and different networks. You can get different paths all the time. Depends on what's available, depends on what's busy, depends on what's cost the less. Okay, cost can be in terms of time, in terms of what's the actual cost of the connection in terms of the amount of bandwidth you're allowed. Okay, but every one of these devices, which are routers, will look at our packet, look at the IP address it's going to, look at the IP address it's coming from, but probably the one it's going to is the most important one. It works out the network ID of the IP address, and then it determines which of its interfaces it should forward out of by looking up its routing table. Okay, the routing table is where all your different networks are stored that you know of. And there's usually what's called a default route as well, which means if it's not in my routing table, I'll send it out of this default route. A bit like our default gateway. If we don't know how to get rid of it or get it to the network, it's not on our network, we send it to the gateway. The gateway deals with it. It's a bit like, yeah, hot potato. I don't know what to do with this thing, but I know that that's the router I need to send it to as my default route. So I just pass the hot potato on, and they can work it out. Not my problem type situation. So characteristics of IP. IP is meant to have low overhead. Overhead is like how much extra bits of information you have to send to get your data across. If you have to send 1 meg of overhead for every 1 meg of data, that's a very high overhead, isn't it? If you think of it as a truck, every ton of groceries you send through your truck, on your truck, there's also the weight of the truck itself and the weight of the trailer. So if you okay? Yeah, just be careful of that. So with the truck, if you like use a big semi-trailer, you just send like 1 box of tomatoes. That wouldn't be good, would it? Because there's a lot of overhead for what you're actually carrying. So IP is also connectionless. What does that mean? It doesn't actually check that the device is over there. Okay, it doesn't know if it's alive or if it's receiving, if it's connected. That's why we can always it's a best effort. We don't check if it's gotten there, and it's media independent. So that's the whole point of having these layers, so that the physical layer does not have to have any relationship to the networking layer. The physical layer, we could use copper, optical, fiber optics, Wi-Fi, anything, but the IP addressing is still the same. Just like at home, you use Wi-Fi. Here I'm using Ethernet, but the IP address for Google is still the same, isn't it? I still go through the same network to get to Google eventually. That's why it's media independent. So connectionless, IP is connectionless. It does not establish a connection with the destination before sending a packet. It doesn't say, hey, I'm going to send you something, and wait for you to reply to say, okay, I'm ready. It just sends it. There's no control information needed. It doesn't synchronize. It doesn't do any acknowledgements, etc., etc. And the reason for that is because it's not its job. Okay, it's not the job of the IP. Remember, before, like with IP, does it always come by itself? Do you always hear IP, or do you hear something else before it? When you hear the protocol name, what's the name of this thing? It's not just called IP, is it? What's it called? So when I go to install something on my protocol, my network card, what is it called? Let's have a quick look. So I've got this, I've got change adapter options, and when I go to my Ethernet adapter, I can actually install and uninstall various protocols. So here's my IPv4, here's my IPv6. I can actually just untick IPv6 and I can remove it. So IPv4, it's not just called IP, is it? What's it called? TCP IP. Okay, so getting back to my point, I know that's a long labored point, but hopefully it makes sense to you. It's not the job of IP to synchronize, to set up a session, to acknowledge and to error check. It's the TCP's job. So IP is just there for addressing information and getting the best trying my best to get it there. So the destination will receive the packet when it arrives. there's no pre-notification sent by IP. If there is a need for connection-oriented traffic, another protocol handles this, and this is typically the TCP at the transport layer, which is the next layer up. Okay, that's the whole point of layers. Each layer takes care of its business, and if each one does its job, then it all works together. So it doesn't need to worry about everything; it just needs to worry about its job. So if we take this analogy as a letter, we just post it. We don't know when it's going to get to the house, or which way it's going to go on the streets to get to the house, as long as it gets there. And when it gets there, it gets there. So best effort. So we send it. We can't guarantee it's going to get there. It's not like certified mail where you sign for it. It's just going to be sent and it's going to be there. But you all know that sometimes letters get lost as well. Okay. So best effort will not guarantee the delivery of the packet. IP has reduced overhead since there is no mechanism for resending this data that it's not received. IP does not expect any acknowledgements. So if I send something and if I want to check if you received it, I'll always go, did you get it? And you say yes or no, right? Then I'll resend it or something like that. But IP doesn't worry about that. IP does not know if the other device is operational or if it received the packet. So it doesn't care. It's not its job. So it's sending IP packet, IP packet, IP packet. Some packets would get here, but some might have been lost. Maybe the connection was down at that point in time and it was lost, or some other reason. But IP doesn't care. It's media independent, so IP is unreliable. So if you haven't noticed, though, it's connectionless, meaning it doesn't know if the other computer is even on. It's best effort, it tries its best, but it doesn't really check if it gets there. So really, it's not very reliable. Someone reliable would be doing all of those things, wouldn't it? So IP is unreliable, so it cannot fix undelivered. It cannot manage or fix undelivered or corrupt packets. IP cannot retransmit after any errors. IP cannot realign out of sequence packets. So what if you send 20 letters, but it all carry a bit of the information? But we all know they might take different paths to the destination. What if they come out of order? What if I get packet 10 first and packet 1 last? IP doesn't care. Okay. IP must rely on other protocols for these functionalities. So when we go to talk about the next layer, the layer 4, that's TCP, that does all of these stuff. IP is media independent, does not concern itself with the type of frames required at the data link layer or the media type at the physical layer. It can just send it over any media. It doesn't matter if it's copper, fiber, or wireless. Each layer has their own job. The network layer establishes the maximum transmission unit, okay, MTU. Network layer receives this from control information sent by the data link layer, and this network then establishes the maximum transmission unit size. So basically just what's the maximum size of the packet. Okay? Fragmentation is when layer 3 splits the IP packet into smaller units. So let's say the maximum units is this much, but my data is this much. I can't fit it in just here, can I? So what do? You just split it up into smaller parts to send. Okay, it's just like, what's a real life analogy? It's just like if you're moving house and you can't put it all in one truck, you just send it over in lots of trucks. Okay, but the problem is that if it's one big piece of information, just having some of it, it's not good enough. Because if you only have 90% of a file, that's not really a functional file. It's a corrupt file, isn't it? So fragmentation can also cause latency, because if I'm sending it in little bits and pieces, who's to say there's one piece might not be delayed, another piece might be getting there faster. So IPv6 does not fragment packets. Example, routers go from Ethernet to a slow WAN with a smaller MTU. So if we go Ethernet here, it might be a bigger MTU, but when it goes from the router to this copper serial, because that's actually slower and the MTU might be smaller, it now needs to chop this up again and re-encapsulate it as smaller packets. So IPv4 packets. So as you probably sort of now getting used to the fact, there's a header. Header is where all the primary useful information is located for how do we get this packet to the destination. IPv4 is the primary communication protocol for a network layer. The network header has multiple purposes. It ensures the packet is sent to the correct destination or direction. It contains information for the network layer processing in various fields. The information in the header is used by all layer 3 devices to handle the packet. So what's in the header? So there's a whole heap of information. Okay, so there's the version, there's the internet header length, there's these things, there's the total length, there's the identification, there's a flag, there's a frame offset, there's a time to live, protocol header checklist, checksum, and source and destination IP address. So what's important? All of these things are important to someone, okay? But for us, the important thing is the source and destination IP address. That's the most important thing, because that's what routers use to determine where do I send the packet next. If I have a destination IP address of this, and that's in my router table, and that tells me to send it out of interface 6, then I will now take this packet and send it out of interface 6. And obviously the source IP address is important as well, because if it's coming from that computer and my friend Randolph, that's his roommate's computer, let's say, and Randolph has decided to create a firewall rule to limit the internet after 12 p.m. so he can have more bandwidth for playing his games, he might just create a firewall rule that any communication from IP address 10.00.1 is actually denied. Okay, so with firewall rules, we can deny on source or destination IP address, as well as source and destination ports, which is the next layer. The time to live is something important, because you know how there's so many routers. How many routers does it go through before it gives up? Okay, how many routers should we go through before it gives up? Because maybe there's just no route to the final destination. Okay, so, or maybe the link is broken that goes to the final destination. So it's just like if we want to get into Melbourne, but there's only one road to Melbourne, and that road is down because there's a major accident. What do? Do we just keep on driving around little roads trying to get to Melbourne, but we can't? Or do we just say we can't go to Melbourne today and just give up? So the time to live is basically a count of how many routers it goes through until it just stops. Okay, don't worry about it, because you can imagine a situation where if it doesn't have a time to live, it would just go from router to router to router to router to router to router, and it will be on there forever, couldn't it? So that's to prevent that. All right, the version will be v4 as opposed to v6. Obviously, v4 for IPv4. The differentiated service, that's where we use for that quality of service. So Jai, if you remember, you talked about quality of service. So this DS, differential service area here, would identify anything that needs higher priority for quality of service. The header checksum, so anytime you hear a checksum, it basically means it's a way of checking whether the thing is corrupt or not. Okay, a checksum is a result you get when you apply a mathematical algorithm to this thing, in this case the header, and it should end up with this result. If you always apply the same algorithm, you always should get the same result if it's correct. If you don't get the same result, then something's gone wrong. So which means this packet's been corrupted, or in this case, this header has been corrupted. Time to live is the layer 3 hop count. When it becomes 0, the router will just discard this packet, so it doesn't just lives on. It doesn't go on forever in loops. The protocol is the next level protocol, the level above it. So layer 4 protocol is the ICMP, is the TCP, is the UDP. And the source IP address and the destination IP address are pretty self-explanatory. They're the IP addresses of the devices that sent it, and also the device it's going to. All right, so we'll do this after the whole presentation. So IPv6 packets. So like I said, we're not gonna focus too much on IPv6, but let's think about why we have IPv6. Let's do some calculations. First of all, So let's, you know how IP address has 4 areas, right? Something dot something dot something dot something. What's the maximum number that can be in each of those areas? What's the maximum number? 255, right? So it can be 0 or any number in between that and 255. So how many different things can it be? How many different numbers can it be? 2 to the power 32, which is 256. No, it's 256, okay? So 0 plus 255 is 256, isn't it? So each one of them can be in one of 256 possibilities, isn't it? So if we just do our simple permutations thing, it's 256 in the first octet times 256 in the second octet times 256 in the third octet times 256 in the fourth octet, and we get 4,294,967,296 possible IP addresses. Okay, let alone that, don't forget, I know you haven't learned it yet, but we'll learn it soon. But there's areas where we are reserved for multicast. There's IP addresses we reserve for experimental, and there's the loopback IP addresses, and there's all these other functions that's reserved. So really, out of the 4 billion, let's just say it's 4 billion. How many people are there in the world? 8 billion, probably close to that now. I don't know exactly, but it's a lot more than 4 billion, isn't it? Okay, we can say that for sure. How many devices do you own right now that may need an IP address? I can see my friend Duvan's got a phone, he's got a computer. He doesn't. Do you have any Bluetooth headphones or anything like that? No? All right. So he's got 2 at least. Okay, but then we talked about like my situation at home where I've got the Ring doorbell, we've got the cameras, we've got the router, we've got the Chromecast, we've got the Google Home, we've got the lights, we've got the fridge, we've got the smart TV. Oh my God, I'm sure everyone these days will probably have at least 5 devices that probably needs an IP address if they all are to be on the same, all to be connected. Okay, so 8 billion times 2, that's 16 billion. You can see that's not enough, is it? 16 does not fit into 4. Okay, so that's the reason. Okay, like it's a bit like the Y2K bug. Why would you need more digits to store the year? You know, you heard about the Y2K bug, guys? So in the old days, they used to store the year in 2 digits. Like if you're born in 1986, then your year would be 86. But obviously, when we had the 2000, if we kept on storing as 2 digits, it would be 00, wouldn't it? So if someone was born in 00, would they be older or younger than someone who's born in 86? Obviously, it's younger because 2000 versus 1986. But if you only stored it as 2 digits, you wouldn't know. It would probably get the opposite result. So that's what it's a limitation because no one thought that they would need more than that at the time. Okay, so 4 billion, that's probably at the time when they invented TCP/IP, was more than sufficient for the amount of computers. But mind you, this is when only military universities had computers. Okay, so it's not enough. Okay, so basically we've run out of IPv4 addresses long time ago. And because of that, we use what's called NAT. We spoke about NAT before, network address translation. All our private networks land now use private IP addresses. So the IP address I use at home could be the same one you use at your house, and same one that someone uses at their work. It doesn't matter. They're all not connected to the same network, so it doesn't matter if it's the same. But the routers does NAT, network address translation, from the private to the public. So that's how it works. So NAT has extended the life of IPv4. But as a result, there's a lack of end-to-end connectivity to make IPv4 survive long enough. Private IP addressing and NAT were created. This ended direct communication with public IP addresses, which means I don't talk to. If I was at home, my computer wouldn't talk to Duran's computer at his house directly. It would be going through NAT on my router, through the internet, and NAT on his router before it gets to him. In fact, I can't even talk to him directly with his IP address because his IP address is not available on the internet. We would have to do something like port forwarding that we described before. Well, why is this a problem? NAT increases the network complexity. NAT was meant to be a temporary solution and creates issues on the internet. Issues on the internet as a side effect of manipulating network header addressing. NAT causes latency, so every time it goes through a NAT, it causes a lag, and there's also troubleshooting issues as well. So IPv6 was developed. Okay, so IPv4 ran out, so we have IPv6. So if we do IPv6, was developed by the Internet Engineering Task Force. IPv6 overcame the limitations of IPv4. So in that case, improvements that IPv6 provides is there's an increased addressing space from 32 bits, which is IPv4, to 128 bits. Let's do some basic calculations again. Where's my calculator? All right, so if we had scientific, our program is fine, scientific. So if it's 32 bits, 2 to the power of 32 gives us that 4 billion, doesn't it? That we just spoke about. Okay, there's just different ways of working it out. Where's my clear everything? Now 2 to the power of 128. You can see it's a lot more. So this means 3 with 38 zeros behind it. Okay, that's billions upon billions. I don't even know. All right. So this is 10 to the 36. That's that many 36 zeros. 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 3 is 36. So that's 1 unidecillion. Oh my God, I can't even pronounce it. So there's 4 billion IP addresses, but there's 340 undecillion IPv6. So you can see that that's a lot more. Okay, if we look at this, it's actually every time it goes by one of these, it's 3 times more. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 3. This is 27 times more, I think. I don't know now. My maths might not be the best, but it's a hell of a lot more. Let's put it that way. Okay, so hopefully we're not going to be able to. Let's actually finish off our maths a little bit. If we had this amount and we divided by 8 billion times, we said 2 devices. Let's say 10 devices. Okay, each person has 10 devices. Divided by 80 billion. Then 1, 2, 3, 4, 5, 6, 7, 8, 9. That's still that many IP addresses. That's free. Okay. So that's 10 IP addresses per person that we sort of worked out roughly. So this improves the packet handling, simplifies header with fewer fields, and eliminates the need for network address translation, because if we got so many IP addresses, everyone gets a proper one. Okay, everyone gets a proper IP address. No need for silly private IP addressing. There's a huge amount of addressing. There's no need for private addressing internally, and be mapped to a shared public IP address. So everyone gets to be on the public. So it's still got headers, but the headers is bigger because there's more room needed for the IPv6 and IPv4. IPv6 source and destination addresses. IPv6 is simplified but not smaller. The header is fixed at 40 bytes or octets long. Several IPv4 fields were removed to improve performance. Some IPv fields were removed to improve performance, such as the flag, the fragment offset, and the checksum. Okay, so we're not going to, like I said, we're not going to focus too much on it, but just be aware that we still got these headers, but probably the most important one is the source and destination IP address and the hop limit, which is basically the same as the time to live. How many hops do we before we say it's enough? IPv6 also contain extension headers. These EH or extension headers provide optional network layer information, but these are optional. They are placed between the IPv6 header and the payload, and may be used for fragmentation, security, mobile support, etc. It's probably for future proofing a little bit. Okay. Yeah. So this is so there's room for future proofing. Okay, so now that we've finished talking about IPv6, let's totally forget about it because we're not really going to worry about it too much. But IPv4, definitely remember that. So host forwarding decisions. Okay, so a router is not as it's a lot smarter than the switch. The switch basically does one little thing. It maps ports to MAC addresses. It knows all the ports and it knows all the MAC addresses because it learns it, like we said. That's all it has, just a table, and that's it. But a router needs to determine what is the network, destination network, not just the destination IP address. It takes the destination IP address and strips it back or does a process and gets the network ID of the destination network. So packets are always created at the source. So remember how we said the frames? They're created on this computer. They're sent if they're communicated. Let's pretend this is one network and you're a different network on that side of the room. Okay. If Marianne has a computer, it has a MAC address. It has a source and destination MAC address. Okay. The source MAC address is Marianne's MAC address. The destination, if she wants to communicate with Javon, and my computer is the router here between the two networks. What do you think the destination MAC address will be? Would it be Javon's MAC address, or would it be my router's MAC address? Right? Yes. Remember what I said, Javon, last week? Is that the MAC address is only used within a LAN, within a network segment. So source MAC address is Marianne's. Destination MAC address is the router interface that's pointing to this network. What the router does is it decapsulates that, opens up the frame to look at the packet. Okay? All right. But let's go back one step. But when Marianne creates before even the frame, it creates a packet, right? So the packet will be source IP address is Marianne's, but the destination IP address is my router, or is it Javon? Javon's. Okay. So IP address is not per LAN. It goes through the whole internet, isn't it? That specifies where it's going. Final destination. So it takes that, it encapsulates it into the packet. In the frame. When the frame gets to my router here, it opens it up. It trashes the old frame headers. It looks at the packet addressing information now. Destination MAC address, destination IP address. Oh, it's on this network here. Now it will make a decision. I'll go from my routing table. The routing table says that if I want to get to this network, I send it out of interface 2. Okay, so now the router will re-encapsulate, make a new frame with a new source MAC address, new destination MAC address. But the source IP address and the destination IP address is still the same. I did nothing to the packet, did I? I just changed the frame. What do you think the source MAC address would be now? What? Router's interface to this network. What do you think the destination MAC address is now? Javon's MAC address. You see how in this step I've decapsulated the frame, read the packet information, and put a new frame together. So that's where we are losing the MAC address information as it crosses the router. But the destination and source IP address remain the same all the way through. Okay? Question? Yep. All right. Packets are always created at the source. Each host device creates its own routing table, and a host can send the packet to the following, to itself, or to the local address, local host destination on the same LAN, or the remote host. So what is this talking about? So again, Marianne. In this case, Marianne is sending a message to 10.1.3 now. Okay, so Marianne's IP address is 10.1.1.2, and V's IP address is 10.1.1.3. So what do you think Marianne's, so Marianne creates a packet, source IP address 10.1.1.2, destination IP address 10.1.1.3, and now encapsulates it into a frame. Source MAC address is Marianne's, obviously. What's the destination MAC address?
It's on the same network, so it would be.
Yeah, it will go straight to V, wouldn't it? It wouldn't involve the router at all. But how do you know, how does Marianne's computer know, should I send it to the router or shouldn't I send it to the router? How does it know? Sorry? Not the MAC address.
For the IP address that they recognize that they are in the same network.
Yeah, so basically, so if that wasn't obvious, guys, let me just quickly, I'm not sure if you guys online can see my screen, but I'm not going to answer that phone right now. But let me just show you something. Maybe I'll show you on the screen instead. Sorry for those guys who got my face. Let's use Excel. All right. So Marianne's IP address is 10.1.1.2, and Fee's IP address is 10. Okay. .1.1.3. But what did I say? Every time you have an IP address, you also have subnet mask. So Marianne's subnet mask is 255.255.0, for example. And then Fee's, subnet mask is the same because they're on the same network. All right. So what happens is a Boolean AND takes place. So what does that mean? It means, in a basic sense, if you're sitting over 255, the number comes straight through. So if it's sitting over 255, it's lined up, the number comes straight through. But if it's sitting like on a 0, the number is blocked and becomes a 0. And this is what's called the network ID. And let's just quickly expand this a little bit. And basically, let's okay, and we'll do that same thing here. So it does this to itself. It knows this information. So Marianne's computer knows this. It knows that its IP address is this, and its subnet mask is that, and its network is that. And now it does the same. It does the same to the destination. Okay, it does the same. So this becomes 10 because it's sitting over 255. This becomes 1 sitting over 255, and this is 1 because it's sitting over 255, and this is sitting over 0, so it becomes a 0. Now it compares this network ID. Are they the same? And in this case, yes, it is. So if it is the same, there's no need to use the router. Okay, if it's the same network, it means I can communicate directly to it, to the other computer. So I just send it to them. But let's just say that this, now it's Jivan she wants to communicate with. Okay, so now Jivan's IP address is that. Very similar, but it's not exactly the same, and this becomes 2. You can see when we do the Boolean AND, we get 2 different results. And because Marianne knows that this and this are not equal, it will send it to the router. So when it sends it to the router, it will use the router's MAC address as the destination MAC address. Is everyone following me, guys? All right. So if you want to get technical, what is a Boolean AND? Let's just do one. If we have remember our binary? So 2 to the 0 is 1. I don't know how to write 2 to 0. 2, 4, 8, 16, 32, 64, 128. Remember that? And 10, what's that? That's 0, 0, 0, 0, 1, 0, 1, 0. Okay, that's that, isn't it? And what's 255? Yeah, so if it's 255, I can know it's 1, 1, 1, 1, 1, 1. So if we say this is the it's actually, so if that is the header, the value of the column, so basically 10 is equal to this binary number, and 255 is equal to this binary number. And when we do a Boolean AND, what's happening is it's in binary, not in decimal, in binary. It's asking a question. Is this number and this number both equal to 1? Yes or no? What's the answer?
Sure.
No, what's yes or no? No, so it's 0. Okay, so you're jumping ahead, Adam. So this one, is this number and this number both equal to 0? No. Is this number this 0? Is this number 0? Is this number but yes? Yes? Yeah. No. Yes. And no. So what's that as a binary? What's that? That's a binary number. If you notice, it's exactly the same as this one, isn't it? Which is equal to 10. Okay. So the equal is a special character, obviously. All right, it's equal to 10. Okay. So you see how that's what it's actually doing. I know I've gone over a little bit over complicated or in depth into this, but the problem is we need to know this because eventually we're going to be doing IP addressing, and we need to understand this. What is the Boolean AND? Okay, so Boolean AND is basically what's called, and that's what you're doing. Another easy way for you to think of it, think of these ones as little arrows. So wherever's on top drops straight down. Whenever it's a 0, it's a block. It blocks that number. Okay. So if we change all of these to 0, let's take that last number 2. Okay. 2 is basically that, isn't it? As a binary number, and it's sitting over 0. That means all of these are zeros. Okay, all of those are zeros. And then when you ask the question, if these are all zeros, it's always going to be 0, isn't it? Because nothing and 0 can never all both be equal to 1. Okay, sorry. Yeah. So are you guys following me, guys? So when we put the subnet mask as 0, this last octet here, whenever it's 0, it cannot be true. If the question is, are both this number and this number equal to 1, if it's 0 down here, it can never be true, can it? So it's always 0. So if you like to think of it, whenever it's 0, it's going to be blocked in a binary way, and it's going to end up with 0, and that's why you got 0 here. And as a result, that's your network ID. All right. All right, so it determines if it's on the same network. If it's on the same network, it sends it directly to them. If it's on a different network, then it sends it to the router. That's how it makes these forwarding decisions. Post forwarding decisions continue. The source device determines whether the destination, so I was just speaking about that, determines whether the destination is local or remote. This local means it's on the same network, or remote on a different network. So that's what I said. The source uses its own IP address and subnet mask along with the destination IP address. And the IPv6 uses the network address and the prefix advertised by other routers. And the local traffic is dumped out of most host interface to be handled by the intermediary devices. Remote traffic is forwarded directly to the default gateway. So the default gateway, which is a router or layer 3 switch, can be the default gateway, sometimes expressed as DGW. It must have an IP address in the same range as the LAN. So basically, remember what we said? Gateway is this door. It has to have one side inside this network and one side outside of this network. So if it has one side in, this IP address on this interface must be the same on the same network as this one. Okay? It can accept data from the LAN and is capable of forwarding the traffic off the LAN to another network. It can route to other networks as well. If the device has no default gateway or a bad default gateway, the traffic will not be able to leave the LAN. So if you don't have a gateway, you can't go off your network basically. No internet, no anything. All host routes to the default gateway. So a host will know the default gateways either statically or through DHCP. So let's just find my command prompt, ipconfig. So I'm getting it through here. So I'm getting my IP address through DHCP, and I'll also get the gateway information there as well. Where were we? Okay. All right. IPv6 sends the default gateway through a router solicitation or can be configured manually. A default gateway static route is a static route which will be the last resort route in the routing table. All devices on the LAN will need to default gateway of the router if they intend to send traffic remotely. And if we actually have a look, that's interesting. Netstat-R, that's one way. Let's have a look at our routing table of this computer. So it's not just the router that has a routing table. This computer has one as well. Netstat-R, was it? Netstat -R. Missing a letter. Gives you the routing table. Okay, so it's got lots of entries because my computer has lots of network cards. Don't forget, we've got the Bluetooth, we've got the Wi-Fi, we've got the Ethernet, we've got the virtual network card VMnet 1 and VMnet 8, and these all have IP addresses and hence have all of this. But if you notice that there's one that says 0.0.0 and net mask of 0.0.0, it basically means anything. Okay, when it's 0 like that, it means anything. If it's not something that's on the local area network, which is like these on-link ones, these are the different networks I'm part of, then I'll use this default route. Anything that's not on these networks will go through the gateway and be sent out of this interface. That's what it means. And you're probably wondering, Alex couldn't get that that command right because you normally use the route print command. Displays the same information. It's just another way of getting it. Okay. Introduction to routers. So router packet forwarding decisions. What happens when a router receives a packet? Its destination is for 10.1.1.10, and it looks up its routing table. So if it's just like the 255.255.255.0, it will know that this is the network ID, right? Remember just what we did before? So if this is the network ID, this is the match. It goes through its routing table and goes, this is the destination. Which of these networks does it match? It's not going to match that. It's not going to match that. Or matches that, but then it knows to send it to router 2. So it just forwards the packet to router 2, and when the router 2 gets it, it will know that it will send it out of this interface 1. IP routing table. So there's 3 types of routes in a routing table. There's directly connected. So if I am a router and I have multiple interfaces, if I'm directly connected to a network, like this side of the room and this side of the room, 2 networks, if I'm connected to this network, I have an IP address on this network. So I know that network. I'm directly connected. If I have another interface that connects to this network, then I have an IP address here as well, and I know of this network, and that's another directly connected network for me. There's also, so any network it's connected to, it's a directly connected route, okay? There's also a remote route, okay? So what does that mean? That means that, hey, I'm also connected to this router here. All right, let's pretend this is a router here, okay? This router here, but this router knows about other networks beyond here, okay? So what routers are configured to do is they are configured with what's called a routing protocol, which then tells my friend routers what networks I know of. For example, I know of this network and this network because I'm directly connected to it, and then I'll use my routing protocol, could be RIP, could be OSPF, and I'll tell the other routers I know are connected to that I am connected to these networks. So they are remote routes for them. The remote routes, these are routes that the router does not have a direct connection to, but may have learned. They may have learned about this manually because the administrator typed in a static route, or it could have learned it dynamically through what's the routing protocols I just spoke about. There's also a default route, like I have no idea what to do. You know, the hot potato situation, spinning my hands, I don't know what to do. I'll just throw it out of this interface because that's my default route. It's a bit like the default gateway of the router, okay? So here, if we take this picture, probably better than my example, router 1 is connected to this network and this network. So these 2 are directly connected. But this network, which is connected to router 2, is what's called a remote network. It doesn't know about this network unless router 2 tells it with a routing protocol. Static routing. Static means it doesn't change. Okay, so it's administrator put it in, typed it in. It doesn't change. It's always there. So, but it must be configured manually. So the administrator has to do something, and it doesn't change. It must be adjusted manually. So if there is a change, the administrator has to make a change manually. Okay, and it's good for small non-redundant networks. You know why it's good? Because I don't need to set up any complicated routing protocols and whatnot. And basically, this is a small network. There's only one link, so it's not redundant. Redundant means there's multiple ways of getting there. So if I just configure there's a network here called this, I know about it. So I will use this command, IP route network ID, subnet mask, and the exit interface or the next hop router. Then I can always do this. Okay, this is just a simple configuration. That's fine. But what if we try to apply here? Here we've got 3 routers, and you can see that if PC1 wants to talk to PC2, I can go through this router, go down this way, or go down this way, and go here, couldn't I? There's multiple ways of getting there. So if I configure a static route to go this way, no problem, it works most of the time. But what if this fails? If this fails, it just means that these packets will never get there. Even though this is still open. It's like you're going to the airport. You only know one way to get to the airport, and the road that you know is what's it got an accident on there. You're not going to be able to get to the airport anymore, are you? Even though other people can go there, you can't. So basically, a static route is no good for a more complicated network where there's redundant links, and you can't adjust the network topology based on what's happening. Okay, whereas if you use dynamic routing automatically discovers remote networks because they learn from each other. They automatically update the information if there's something changes. So in this case, router 1 tells router 2 about the network it's connected to. Router 2 tells router 1, no problem, simple network, works there. But here, they just tell their adjacent routers. So router 3 tells router 1 and router 2, and router 1 normally will go through this way, but because that's down, router 3 is also advertising the routes it knows about, because router 2 is told router 3 about this network. Router 3 can also tell router 1 about that network it knows about. So now it automatically adjusts its route to go around that broken link. You see how they can compensate or adjust to the new topology very quickly and easily, and you don't have to do anything. Chooses the best path for destination, finds a new best path when there is a topology change. Dynamic routing can also share static routes with other routers as well. Okay, so let's have a look at this. This is an example of a router, and it's doing the show IP route. So the show command just basically displays information. And if we look at this, this is the results. You can see there's a S. S stands for static route. So there's a default route which is configured as static. So if I don't know that this network, I'll just send it out of this, send it to this next router. So if we're here and 2.6, so it has 2.6 is this router 2, I'll just send it there. But I know about 10.1.1.0. Where's that? I don't know. But I know about that because I learned this one. O stands for, where's the O? There it is. So this is a ODR, periodically downloaded. No, sorry, this should be this O. That's the weird O. It's not that O. It's O for OSPF. That's one of the routing protocols. And we got the C, which is the directly connected networks, and the L stands for the local link on that network.